Hi, this is Paladugu Keshav of CSC Data Science, and our subject is linear algebra and calculus. Today's our topic is state estimation and observability analysis based on echelon forms of linearized measurement models. We are we are going to have a small introduction about our topic. State estimation is a real-time function responsible for mapping error corrupted telemetry data to a reliable error-free database information in modern computerized power system. It comprises basically three tasks: measurement noise filtering, bad data detection, and identification and observability analysis. State estimation is a real-time function responsible for mapping of error corrupted telemetry data into reliable error-free database information in modern computerized power system control centers. It comprises basically three tasks: measurement noise filtering, bad detection and identification, and observability analysis. The most used method for power system state estimation is one based least square criterion. The main reasons for that choice and nice statistical properties and simpler conceptual problems method presents a very efficient noise filtering ability but fails in case of bad data. Bad data detection and identification methodologies based on hypothesis tests of measurement residuals and exhaustive search can be added to the basic LS estimator to make the algorithm more reliable for practical applications at an expense of conceptual efficiency and simplicity. Other types of estimators have been proposed to overcome the difficulties encountered in basic LS method. The first one is bad data suppression. BDS estimator uses a non-quadratic criterion and can be implemented with minor changes in LS-based estimator code. Exhibits reasonable bad data suppression ability but convergence difficulties in some cases. Least absolute value LAV estimator chooses a solution which satisfies exactly a non-redundant set of measurements can be formulated as linear programming problem, presents a bad data suppression capability similar to the BDS estimator but a much more robust convergence characteristic. Least median of squares LMS estimator. It is a brand new approach to power system estimation. It uses a combinational procedure to calculate the least median of squares to weighted residuals of non-redundant samples of measurement set. Their authors claim that it is able to handle divergence points for which the above estimators fail in its present form. It is bound to require excessive computing time in online applications. Now we are going to discuss about problem formulation. In formulation, there are some types. First one is observation model. The static state estimation problem is based on following observation model. Z is equal to h into xt plus omega, where z is a m into 1 measurement vector, xt is a n into 1 true state vector, hx is a m into 1 vector of non-linear functions, omega is a m into 1 measurement error vector, and m is a number of measurements and n is a number of state variables. The usual choice of state variables are voltage phase angles and magnitudes, while the measurements are active and research branch flows node injunctions and voltage magnitudes. All the methods used in the power system state estimation rely on interactive solutions based on linearized versions of first equation. Moreover, it has been found 1, 2 that are fast decoupling techniques applied successfully in the Newton-Raphson load flow algorithm. Works as well in the state estimation problem on account of these facts. The methodology described in the paper based on the incremental decoupled version of the model given in first equation, which is represented by equations. Delta Zp is equal to Hp delta theta Te plus omega p. Delta Zq is equal to Hq delta Vt plus omega p, where theta T n theta into 1 Vt into Nv plus into 1 are vectors of true values of voltage magnitudes and phase angles. PQ are subindices indicating partitions of vectors and matrices corresponding to active and reactive measurements. HP and HQ are constant submatrices derived from delta H and delta X calculated in nominal conditions. N theta is equal to n minus 1, Nv is equal to n, comma, and n is a number of network nodes. Both LS and LAV estimators use global function of residuals norm as a criterion to define the best approximate solution to equation 4. The most effective methods so far proposed for bad data detection and identification are based on the analysis of individual residuals or group of residuals rather than on the global function of residuals. Therefore, it seems to be reasonable idea to develop estimation method which chooses as a best approximate solution to equation 4, one such that the individual residuals satisfy the certain conditions which indicate that the state estimation has been achieved. The LAV estimator chooses the solution which satisfies the exactly n theta equations, basic measurements or basis the minimizes the sum of the absolute value of the remaining MP minus n theta redundant measurements residuals. The minimization process itself is not quite necessary. It would be enough to be residuals corresponding to measurements of the chosen to be satisfied exactly to have absolute values less than the tolerance. If this was not so, better basis should be selected and so on until a satisfactory solution is reached or process fail. Non-linear estimated algorithm. Non-linear estimated algorithm is modeled in one can be solved in a block interactive process in which the iteration consists of solving the two linear estimation problems represented by 2 and 3. The iterative process is stopped when the absolute value of the components of delta theta and delta v fall down below the given tolerance. As usual, in the power system, state estimation literature is assumed that the properties of the given above are linearized problem solution are valid approximately for the state obtained which this interactive process. Therefore, it is possible to test the normalized residuals corresponding to the converged solution in order to assure that it is not corrupted by round of error. If this is not so, the other basis should be selected as explained earlier in this paper. Based on the above assumptions, in non-linear case, it is only necessary to calculate the residual vector R after the interactive process has been converged. Therefore, in equation 11, only need to update it in every interactive step. The non-linear estimator is presented in following algorithm where ZP, ZQ, HP, HQ and our convergence tolerance are assumed. And here is the algorithm. Basic measurements and choice and basis change. Now we are going to discuss about in the absence of bad data, any non-redundant set of measurement could be chosen in principle as the basis. However, owing to possible ill conditioning of HP, and to assure a more accurate state estimate, some care should be taken in choice of basic measurements. Moreover, information about measurement reliability is often available in practice, which also must be considered in choosing the initial basis. The important examples of these information are exact zero injection pseudo measurements, which must always included in basis of flow measurements in low impedance in lines, and injection measurements in buses connecting several high and low impedance lines, which are conducive to leverage points according with not be included in the initial basis unless they are critical for network observability. Bad data processing. The bad data processing is a problem. Bad data processing is a problem associated with the estimation estimator introduced in paper is similar to the one studied for LAV estimators. For these estimators, the state estimate affected only if the bad data is in basic measurements. In this case, the measurements contaminated by the bad data should be exchanged with the healthy redundant measurements. However, the identification of which the set measurements is contaminated with bad data is not trivial, as have been demonstrated previously for LAV estimators. Now we are going to discuss about bad data detection. Bad data detection is performed by the same validation criterion described in section 3.3 for detection of unacceptable estimates due to round of errors. In the implementation of reported in this paper, both problems are tackled simultaneously. Measurements which are not actually bad data but produce ill-conditioned HB matrices should be identified by an offline study using stimulated data. The validation criterion should be introduced in section 3.3 is by no means the only one which can be used with the methodology proposed in this paper. Better criteria combining previous experiences with LS, LAV and LMS estimators may improve considerably a bad data performance of proposed estimator. Now we are going to discuss about bad data identification. The exchange of basic and redundant measurements in the mechanism used for bad data identification. The identification criterion is based on the fact that bad data is one of the which does not fit well in a model developed assuming only good data. Therefore, if bad data is introduced in basis, several healthy measurements will present the large residuals. On other hand, if the bad data is taken out of the basis, healthy measurements previously exhibiting large residual will probably present residuals within the confidence threshold. Of course, these assumptions are valid only if local redundancy is high enough to the number of bad data small compared with the number of good measurements. And here is the geometric interpretation of bad data identification process. Now we are going to discuss about tracking mode operation. The present trend in online state estimation is towards an incremental update approach, i.e. very fast solution of state estimation problem to take into the account of small changes between two measurement snapshots. Execution intervals of 4 to 10 seconds are envisaged by some users in order to obtain such speed. Bad data detection and identification techniques based on the measurements and state forecasting ought to be used. The techniques are able to indicate measurements prone to the bad data. The estimation method described in this paper can easily incorporate this type of information by just avoiding the inclusion of such suspicious measurements in basis. This approach will reduce substantially a bad data processing requirements. Now we are going to discuss about results of simulation studies. The simulation studies the simulation studies reported in this section were performed in Unisys A9P computer with a 32-bit single precision floating point number representation. The programs were written in standard Fortran language, which the test users to used in studies were standard IEEE 1430 and 118 bus systems. The usual procedure to adding a random errors to exact the results of a load flow solution as defined in 9 was used to generate the measurements. The measurement configurations used in the sample of results shown in the section is summarized in the table. 1. In the configurations, these active and the reactive measurements of flows injections always appear on the Paris. The most of these configurations have been used before to test other methodologies as referenced in the test case column of table 1. Now we are going to discuss about state estimation results. The results of state estimates the obtained with the methodology described in the section 3 for measurement sets without a bad data were compared with the results obtained with a decoupled version of the weighted LS estimator. The comparison was made in the terms of average and maximum percentage error in this state variable when compared with the true values. In table 2 presented a summary of results for the selection of tested cases. The results shown in table 2 confirms the less effective filtering ability of the proposed estimator in comparison with a weighted LS estimator. However, the results are still acceptable for practical applications. The larger errors presented in the case G for both methods should be credited through a high sensitivity of the percentage error in a phase angle, particularly in a case of small angles. Now, here is the table about the percentage error in estimations. Now, we are going to discuss about observability analysis results. The observability analysis methodology described in section 4 was applied to several test systems and measurement configurations, including the 9 test cases shown in the table 1. For cases A and D, the results obtained were the same as ones reported in 15, 18, 20. For the other cases, the results obtained coincide with the results from the test performed with an observability analysis program developed according to the methodology proposed in 1718. In both sets and tests, the single precision arithmetic was used to threshold the below which the elements of factorized matrices were considered 0 was set to 10 power minus 4 pu. Now we are going to discuss about bad data processing results. Several bad data processing experiments were performed using the test system described in the table 1. As a sample of most relevant results is presented in the table 3. In this table, only results for the 14 and 30 bus systems are presented for a lack of space. Similar results were found for the 118 bus system. The results were shown in the table 3 indicate the methodology is able to detect the most of the simulated bad data. However, failed in few cases. And here is the table about bad data processing results. And here are some general comments. In its present form, the method is introduced in paper, presents in conceptual requirements comparable to the LS approach. If, if the fact, and now we are going to discuss about conclusions. This paper has introduced as alternative approach to the power system state as estimation and observability analysis. The proposed methodology is based on the factorization of the linearized measurement models in the echelon form. From this form, the state estimation, observability analysis, and the bad data processing can be performed under the same algorithmic framework. The proposed approach offers a novel way of understanding the addressed problems and opens up the possibilities of aggregation previously introduced knowledge in the subject. The results of simulation studies showed and the proposed method for the potential for online applications. Further research and improvement of the validation criterion and the conceptual technique to obtain the update the echelon forms may considerably the performance of the proposed methodology. Thank you.